dropped in. Hopefully it won't be too messy to have two separate recordings, but
so have to splice them together.
yeah, we can split. Someone that knows how to use technology can do that. I think it's recording already. Does that seem like the case to other people?
It is, yeah.
Yeah.
Okay, great. Yeah, so anyway, so we define these Schubert cells as just like nice homogeneous spaces. And in order to find the dimension, what we're gonna do is we're gonna look at the tangent space. So we're gonna look at sort of the Lie algebra version of this. So the tangent space of sort of this homogeneous space upstairs is just going to be the same thing, except everything with the Lie algebra is replaced. So I guess I'm being slightly sneaky because Saad is back.
Sorry, Wi-Fi broke, but it seems like the recording is safe.
Yeah. Okay. So that sounds good.
Back on, but we may have just missed the past couple minutes of the recording. My bad.
Well, I think we only missed like a few seconds at the most because people pointed it out.
Yeah.
Pretty cool. So I think we're good. Okay. But anyway, so we look at a tangent space, and that's the same thing, except we kind of switch all the Lie groups with Lie algebras. And now we want to compute the dimension of this. So, well, how are we going to do that? So essentially, it all just comes down to computing the adjoint action of this T lambda on Lie algebra GO. Well, so we know for sure that the adjoint action is going to respect the root decomposition. We also know that the adjoint action is going to act by the identity on the Cartan. So that part we don't need to worry about. So we can sort of break this up into root spaces, and we can like ignore the Cartan. We can only think about sort of non-trivial root spaces. And just kind of doing that, we get that this is isomorphic to the direct sum over roots, that's all roots, just to be clear, of G alpha of O mod G alpha of O intersect add P lambda or G alpha O. So we didn't do too much. All we did is we added an alphas. And now we just want to think about how T lambda acts on sort of a single root space. And we also kind of know what that does, right? It acts on the root space T alpha by the weight or by the root alpha itself. So T lambda is a co-root, and then alpha is a root. And basically what we're going to get is that we're going to basically have the action on that root space just be the composition of those two. So in particular, we're going to get that we just have something that looks like this. T to the alpha lambda G alpha O. So this might be a tiny bit confusing. It took me a second to figure out why, but if you sort of follow through the definitions, I actually think it makes sense because basically we have the action on the root space is just given by composing the co-root that's coming from lambda and then the root that's coming from alpha. And the way we literally define that pairing is like if you compose a root, a co-weight and a weight, generally speaking, you'll get a map from C star to C star, which will just be T to some power. And we took that power to be the pairing. So we get this. Now we just need to sort of figure out the dimension of these quotients. So these G alpha O's in general, they sort of have their degree in T is bounded below at 0, but not bounded above. So if alpha paired with lambda has a negative power or it's negative, then that space is just going to be 0. The quotient is going to be 0. If it's positive, we're going to have a dimension equal to exactly sort of the value of its pairing. So we get that dimension. And lastly, we want to notice that because we chose lambda to be dominant, the ones where alpha comma lambda is positive are precisely the positive roots alpha, and the other ones will all be negative. So we can just throw out all the negative ones. That's something sort of Saad told us, that dominant weights or co-weights are the ones which will give you something positive when you plug in any simple root or co-root. So we get the dimension of, I'll just write dimension of this thing here equals a sum over all the positive roots of this pairing. And by definition, that's just 2 rho times lambda. So that's it. So if some of those details were a little bit confusing, I wouldn't worry too much about it. I think if you go back and look at it, this is also in sort of in Xinwen Zhu's paper, if people want to look there. It might be a type of argument that helps to look through a second time, but yeah, if you were confused about something, don't worry, because most people just take for granted that that's the dimension of Schubert cells anyway. But it always made me feel like rho just sort of appeared out of nowhere, and I didn't like that, so I decided I was going to prove it. But it won't be super important. So moving.
So Alberto, rho is defined as the sum of all, the sum of the evaluation on lambda on all of these positive roots.
So rho is just defined as the sum of positive roots. So evaluating would be the same as evaluating on all the positive roots, then summing it up. Sorry, 2 rho is the sum of all the positive roots.
Oh, okay.
Yeah, 2 rho is the sum of all the positive roots. Yeah, it's a little bit confusing because 2 rho is the sum of all the positive roots, and then rho is half of that, which isn't always a weight, so it gets a little bit weird. But rho turns out to be really important, so people still tend to write 2 rho for like the sum of all the positive roots. But yeah, great. Okay, so sort of additionally, we want to talk about the closure relations that we have here. So additionally, we have that the closure of a Schubert cell, so fun fact, the closure of a Schubert cell is usually called a Schubert variety, is the disjoint union of all the ones which are less than it. So disclaimer, which I think Saad already gave, but which is worth giving a second time, these less than relations might not be exactly what you'd think, because if 2 weights are not in the same coset of the co-root lattice, if 2 co-weights are not in the same coset of the co-root lattice, then they'll be incomparable, incomparable. So for example, in SL2, if you look at the roots, they're plus and minus 2. So if you take an even and an odd weight, they're incomparable, even if like as integers. Well, obviously as integers, one's gonna be bigger, but as weights, they're incomparable. So in particular, if we have 2 co-weights here, which are in separate cosets of the co-root lattice, they're always going to be incomparable. And this is sort of going to tell us that the connected components of GR are labeled by the co-weight lattice mod. I'm just going to write co-root lattice. Different people write it different ways, but that way no one will be confused. So it's usually not, so the Afan-Grassmannian is usually not connected in particular. But even if you start with a connected group, it's usually very much not connected. And now within a component, any 2 co-weights where they have Schubert cells in that same component will actually, they won't necessarily be related, but they'll sort of at least be some weight that's bigger than all of them and some weight that's smaller than all of them. So within the components, we have something we have a stratification. And sort of the final thing we're going to say about this is that, I'm just going to write it, is that we have GRG is just the co-limit of these Schubert varieties. And each of these Schubert varieties is just like a, finite dimensional scheme, and is on end scheme. So that's very important for sort of proving technical things, even if we might not really cite it too much throughout. But so that's it for sort of the standard stratification, or the stratification by Schubert cells and Schubert varieties on the Afan-Grassmannian. Now we're sort of going to go ahead and talk about another perspective. So maybe this is a good moment to see if anyone has any questions.
Yes, Surya has one.
Great.
he asks, could you describe the orbits and the closure relations explicitly for SL2?
Yeah, sure. Let me, I'll just erase this. Yeah, so for SL2, we know that the weights look like Z, and sort of under that isomorphism, the roots are plus or minus 2. The co-weights also look like Z, and just for extra clarity, I'll just sort of write like the generator, the one which we usually think of as 1, is just sending T to T inverse 0, 0. So, and I guess I could even just write like sort of the nth one is usually just that. It turns out that the co-roots are sort of plus or minus 1. So we actually have a somewhat anomalous case where the co-root lattice and the co-weight lattice correspond. So there's only one connected component, and in particular, if we just label these Schubert cells by integers, then we will literally just have sort of GRN is contained in GRM closure if and only if n is less than m. So yeah, I think in general it's always like a good sanity check to make sure things work for SL2. That doesn't always mean it's true in general, but it's a good sort of sanity check. So does that answer? Sorry, yeah, does that answer your question? I guess your mic isn't working, but yeah, great. Okay, yeah.
Sorry,
no, I think it's
with this thing that you just said, I thought that you were saying previously that it had to do with the parity of M and N.
Yeah. So
but, I mean, that's the ordering with respect to.
Yeah, no, that's fair.
Not just integers.
Yeah, I was a little bit sloppy there. So if you're talking about the ordering of the weights in SL2, then you'll get that like 4 is not greater than or equal to 3. But if you're talking about the ordering on the co-weights, then since the co-roots are plus or minus 1, like.
Oh, okay.
Yeah. So yeah, I was just sort of trying to go for the simplest example, and the simplest example was the weights of SL2, not the co-weights of something. But yeah.
I have a question.
Yeah.
So if you did PSL2, then would the affine Grassmannian have 2 connected components?
So I think you mean PGL2? Because,
yeah.
Yeah, if you did PG, so I think Saad just mentioned this. I mean, but I'll just sort of, PGL2 is the language dual group of SL2. So yeah, I mean, precisely. So the co-roots and the co-weights of PGL2 are just the roots and co-roots of SL2. So yeah, GR PGL2 will have 2 connected components. And yeah, and within each connected component, the Schubert cells will correspond to integers of a certain parity, and then there the closure relations will just be the usual closure relations among the integers. So yeah, so we sort of went through 2 examples in the end, which I think is super good. Yeah, I mean, these, yeah, great. Okay, does anyone else have any questions about what we said so far?
Yeah, Alberto, I had to get up for a second. Can you scroll up to the previous page so I can quickly take a look at what you wrote?
So yeah, Kenny, I don't know if you were there for sort of the end of when we're proving the dimension count, but then we just sort of described the closure relations, and then that gave us the connected components. And we noted that we can take the affine Grassmannian as a co-limit of Schubert varieties. Get that's an in scheme.
What are the morph, like, what is this co-limit over? I guess,
yeah.
So I see. So you have this relation between the 2 of them, and then you just get an arrow for each.
Yeah, exactly. You get an arrow. Every time there's a co-weight, which is less than or equal to another co-weight, you get an arrow. Exactly. And we showed up here that every time you have a less than or equal to, it means one's included in the closure of the other. So since we're taking the co-limit of the Schubert cells, we're good. But yeah, I mean, that's a good question. I definitely, if I was being fully formal, I should have written that somehow, but I couldn't think of a super evocative way to clarify that those were the arrows. But
no, you're good. I mean, yeah.
But yeah, great. Yeah, so I mean, that's a good point to make. Yeah, I mean, when you take a co-limit in general, you do need to think about what the arrows are too.
Thanks.
Also, just for the sake of maybe saying another word about that. There is a way to just do this where you take a colimit over, say, the integers. You can look at, say, all the Schubert cells, all the Schubert varieties of a certain dimension, and just put those all into sort of one thing and just take the colimit of those. And there are other ways to do it. We might even get to talk about another way to do it today. But okay, any other questions? Okay, I'm going to take that as a no. Cool. Okay, great. So now we're going to have an interlude. Though it's an important interlude, but it's sort of a deviation from what we've been doing, which is sort of another perspective on the affine Grassmannian. Okay, so let's say we have a G bundle. So this sort of another perspective is going to be everything in terms of moduli space of G bundles, but which is not as scary as it sounds, hopefully. Say we have a G bundle on two formal disks glued together away from the origin. So like glued away, so glued on like these star. So how can we sort of think about this G bundle? So one way we can think about this is we can think of this as two G bundles, E1 and E2 on disks. Let's even name the disk D1 and D2, plus an identification beta from E1 restricted to the punctured disk of D1 to E2 restricted to the punctured disk of D2. So essentially I'm saying these two are the same thing. Also, let's call this weird two disks stuck together ravioli thing detailed up. So yeah, having a G bundle on these two disks glued together is the same as having a G bundle on each one, and then sort of a gluing datum on the star on the punctured disk. So let's say we maybe want to get a slightly more concrete description of this. So we can trivialize E1 and E2. So every I'll just say like every G bundle on the formal disk is trivializable, but it's still important what trivialization we pick. So we can trivialize E1 and E2 and then view beta as a map from the punctured disk to G, i.e. an element of GK, as we talked about at the very beginning when we were dealing with notation. That's sort of the functorial perspective, but we can just say a map from D star G is the same as an element of GK. So what's going on here? Well, if we trivialize both E1 and E2, then we sort of identify them with just the trivial bundles, like G cross the disk. And now we have sort of an identification between two trivial bundles. And then we can just look at, say, where the identity section goes. And then we'll get a function from D star to G. But we actually need the trivializations to do this. However, the annoying thing is that, or maybe it's not annoying, but however, beta is only defined up to a change of trivialization. So we needed to get these trivializations to sort of think of beta as a concrete element of GK, but beta does not depend on the trivialization itself. So really what we get is we get sort of, I'm going to call this inv beta, but we get an element of GO double cosets of GK. So changing the trivialization is going to correspond to multiplying by an element of GO, either on the right or on the left, because a trivialization, maybe I should have written this before, but a trivialization of I'll just say E1 on D1, a trivialization of a bundle on the disk, is a map from D1 to G, or I'll just say from D to G. I.e. an element of GO. So this can be a bit confusing, but essentially we have this G bundle in terms of two G bundles on a disk and identification. In order to sort of get it more concretely, we want to pick trivializations of the two G bundles on the disks. Then we can think of this identification as just an element of GK, but then we have to mod out by choosing different trivializations, because we needed a trivialization to get an element of GK, but B does not depend on the trivialization. So we sort of get that these G bundles on these weird two disks glued together are in correspondence with these double cosets. So these double cosets just keep appearing. And for good measure, let's just remember that these double cosets are the same as dominant weights, co-weights. So now let's say we actually want to recover GK. So if we want to recover GK, or if we want to get GK, say as a moduli space of some kind of bundles, all we have to do is just keep track of the trivializations. So if we want to recover GA as a moduli space of G bundles, just keep track of the trivializations. So actually have them be like real data that's included. And then we get sort of our first thinking of something we thought about before as a moduli space of G bundles, which is we can think of GK just as G bundles on G tilde, which was these two disks stuck together, plus I'm just going to write trivs for trivializations on let me name this G bundle. So E, let's say a G bundle on this, plus trivializations on E restricted to DI. So we managed to recover G. Okay. So now let's say we want to recover the affine Grassmannian. Well, so one thing we could do is we could try to mod out by GO. So that's basically going to be equivalent to forgetting one of the trivializations. And in fact, if we forget one of the trivializations, then we will get sort of a moduli space, which we can think of GO, of the affine Grassmannian as. It turns out there's an even simpler one, which is the one I'm going to write here. And this is actually what a lot of people just take as the definition of the affine Grassmannian. But you take E, a G bundle on the formal disk, and then beta, an identification away from the origin with the trivial G bundle. So E naught is the trivial G bundle. So how do we want to think about this? Well, essentially what we want to think is we have a G bundle on the disk, and we have a trivialization of it on D star, on the punctured disk. So in order to get a function from D star to G, what we have to do is we have to pick a trivialization of the whole G bundle, then we'll get an element of GK, but then again, we need a mod out by the choice of the trivialization, because the choice of trivialization doesn't actually change beta, but it was needed in order to construct an element of GK out of beta. So this gives us GK mod GO like that. But in a sense, these are sort of both, like some people start with this, the definition. These are both definitions which are sort of highly valid.
Alberto, can I ask some just notational things? So yeah. D prime and D, what are what's the difference between?
Yeah, that's a very fair point. I think I did a slightly bad job explaining what D prime was. So D is always just the formal disk, so spec of power series. D star is the punctured formal disk, so spec of K. D tilde is these two disks glued together along D star. So I sort of wrote it here, I think, or I meant to write it, here. But it's actually probably not the best notation because D tilde looks kind of similar to D star. But yeah.
Wait, tilde, or that's an apostrophe to me, is it?
What would you call that?
I would call it like an apostrophe.
D prime.
D prime, yeah.
Yeah, D prime.
Sure, yeah, let's say D prime, yeah, okay. Yeah, so D prime is gonna be two formal disks glued together away from the origin, yeah.
Okay.
So, yeah, so I guess one more thing to say about this is that we can sort of recover these Schubert cells by just having Schubert cells are just the elements of the affine Grassmannian now thought about like this, such that this inv of B equals lambda. So remember we saw how if we had a isomorphism of two G bundles on the punctured disk, we can recover a double coset from there, and the double cosets are the same as dominant cohorts. So for me, it's helpful, sort of this motivation of thinking of it in terms of these two disks stuck together. But a lot of times we're going to want to think of this stuff as in terms of G bundles on curves. So for that, we're going to have to use a theorem called the Laszlo-Boville theorem, which is going to help us out. And I'm definitely not going to prove this theorem, but we're going to use it. And I'm going to state it in two parts. So I think it's not too hard to derive sort of one of these parts from the other, but we're just going to state them both. So X is a curve. So if you have sort of E a G bundle on X, and then beta a trivialization on X minus just a point X, so little x is a point, then there's a restriction map down to let's say to E a G bundle on the formal disk around X, and beta a trivialization on the punctured disk around X. So so given a curve at any point, you can choose a local coordinate and thus get like a formal disk centered at every point. So yeah, so we have this restriction map, and it's literally just given by restricting a G bundle from the whole, a G bundle on the whole curve X to a G bundle on a formal disk around a point. And then we had a trivialization on the whole curve except for that point. So now that just becomes a trivialization on the punctured disk around that point. So the Laszlo-Boville theorem states that this is actually an equivalence. So this should be somewhat surprising. It essentially tells us that if we have a G bundle on a whole curve and a trivialization away from a point, all of the data is local around that point. Sort of the extra data of the bundle on the rest of the curve and the trivialization on the rest of the curve actually isn't contributing anything. However, sometimes just notationally, or not just notationally, like sometimes it's going to be very useful to write the affine Grassmannian as the first thing. And secondly, so this is sort of an extension of our intuition where a G bundle on two disks glued together is a G bundle on each one plus an identification. We have that a G bundle on X is given by a G bundle on dx, let's say a G bundle E1 on dx, a G bundle E2 on X minus a point, and an identification beta from E1 restricted to the punctured disk around that point to E2 restricted to the punctured disk around that point. So this is sort of, again, the analog of how we could get a whole G bundle on two disks glued together by having a G bundle on each one, then gluing them. But this is much stronger. It tells us that we can get a G bundle on the curve by having a G bundle on a formal disk of a point, a G bundle on the complement of that point, and a gluing on the punctured formal disk around that point. So it's not super surprising, I think, that we could get a G bundle like this. I think what's more surprising is that we can get every G bundle like this. So yeah, so that's the Laszlo-Boville theorem. And this theorem is going to give us sort of yet another way of thinking of these GK and the affine Grassmannian, but in terms of a general curve. So I'm just going to go ahead and just write it. So now we can think of GK, given any curve, as sort of E, a G bundle on X, nu, a trivialization on X minus a point, and mu, a trivialization on dx. So it's the same thing where to get the G bundle, we had to have these two bundles and glue them together. To get an element of GK, we have to keep track of the trivializations. The argument, once we have the Laszlo-Boville theorem, it basically tracks like what we said at the beginning. And then the affine Grassmannian can be given by this moduli space. So E, a G bundle on X, and nu, a trivialization on X minus a point. Great. So in a sense, now we sort of produced two new ways of thinking of the affine Grassmannian. One, a local one, and one sort of a more global one for every curve. But they're both true, and they're both important. So as an example, let's see what happens when we take X to be the affine line. So sort of the simplest curve. So just sort of using what we have above, we know that the affine Grassmannian is just equal to G bundles on A1 plus trivializations on A1 minus a point. But now we're going to try to kind of go backwards and get something, again, more matrix looking out of this G bundle version. And when we go backwards, we're going to get something slightly different. So again, so how can we sort of recover a more matrixy definition from this? Well, once we pick a trivialization of G on A1, and every bundle on A1 is trivial, just like on the formal disk, every bundle on A1 is trivial. So we can always pick a trivialization. And then once we pick a trivialization, then we're going to, along with our trivialization along with nu, we're going to get a map from, so let me write this down in words. So once we pick a trivialization of E, we get a map from G to A1 minus, actually even just gonna say this point is 0, to A1 minus 0, but then we have to mod out. We mod out by the choice of trivialization. So what does that mean? It means that the affine Grassmannian is isomorphic to maps from G to A1. So what are those? Those are just G of K TT inverse. And then we want to mod out by trivializations on the whole of A1. That's maps from G to A1. And what's that? That's G of KT. So this is a statement which might be a little bit surprising, but this sort of is kind of a global analog of the local definition in terms of Laurent series and power series that we usually have for the FM. Yeah.
What is this map G to A1 minus 0 that we get?
Yeah, so it's sort of similar to what we were doing before, but basically we have already a trivialization of the G bundle on A1 minus 0. Mm-hmm. So once we pick a trivialization of the whole G bundle, that'll just give us a map from G to A1 minus 0. So
I think the map goes backwards. Is maybe that the issue?
Oh, yeah, that is the issue. Yeah, that is very much the issue. My bad. Yeah, we get a map from A1 minus, I might have said a couple of things backwards, but yeah, we get a map from A1 minus 0 to G. Yeah, no, exactly, yeah. And that's exactly what we're going to want, right? Because those are maps from spec of K TT inverse into G, and those are K TT inverse points. Yeah, great. And yeah.
Yeah, I also have, I guess, a couple questions above. Namely, like, there's this ind B that you defined that I didn't quite catch. Like, I didn't quite see how, I think it was just trivial, like, there's this identification between the your E1 restricted to one punctured formal disk and E2 restricted to the other one once you identify them. I didn't understand how that gave you, or how you associated an element of the double coset with that.
Yeah.
Am I understanding that right?
Yeah. No. Yeah,
Okay.
we can definitely talk about that. So that's sort of up here. So yeah. So we're trying to sort of. So our starting data in this sort of narrative here, I guess, might be the best way to describe it, is our starting data is we have a G bundle on D prime, which we were thinking of D1 and D2 glued together away from their origins. And then that data is the same as a G bundle on D1, a G bundle on D2, and a identification of those two G bundles away from the origin. So now, once we pick trivializations of both E1 and E2, we can view beta as a map from D star to G, because yeah, we can sort of compose the trivialization of D1, I guess restricted to the punctured D1, with beta, with the trivialization of E2, and we'll just get a map from G cross D star to G cross D star. And then we can look at, say, where the trivial identity section is going to, and we'll just get a clean map from D star to G. The issue is then, so given sort of that data starting with a G bundle on D prime, we will get an element of GK, but in defined element of GK, we have to pick trivializations of E1 and E2. And yet the bundle itself does not depend on those trivializations. So then we had to mod out by those. And each of those choice of trivializations is itself a map from DI, from D1 or D2 to G, i.e. it's an element of GO, and sort of post-composing or pre-composing with a change of trivialization will be multiplying your element of GK by an element of GO on either side. So the only sort of well-defined information that we get out of this G bundle is an element of the double coset space.
Okay, I see.
Okay, cool. Yeah, that's definitely, yeah, okay, cool. I'm even glad we went through that again, because that's kind of confusing. But yeah, so I guess sort of returning here for a second.
Sorry, can you scroll back up?
Yeah, we can stay here for as long as.
No, so you're defining that in the beta, that's what you defined it as? It's like the map we get by this formal recipe? Oh, okay.
Yeah, that's how I define it in beta. Yeah, maybe I should have written like a colon equals or right define or something. And just write define right there. Yeah, that's the definition of inf beta. Yeah, I guess that was kind of unclear. And then later on, we sort of used inf beta to recover our Schubert cells over here. Because each of these betas is still like an identification between two bundles on D star. So yeah, I mean, it just sort of gives us a way of defining Schubert cells straight from this definition without having to go back the other one.
So wait, Alberto, maybe Charlie had a question that he wants to ask. I'm not sure. Charlie, do you have a question?
Yes, I do.
Oh,
Yeah,
okay, go ahead.
Can you go back to the Laszlo Boville theorem?
Yep, right here.
Is X affine?
X is not affine. There might be some like slight niceness conditions on X, which I'm brushing under the rug, but you can definitely use any Riemann surface.
Wait, so are you saying that map is an equivalence?
Yeah, the restriction map is an equivalence. Yeah, that's the content of sort of part one.
Then,
like that, yeah.
I feel like I'm misunderstanding something, because like say X is P1.
Sure.
So there's lots of different like say G bundles on P1, say if G is SL2, right? So like any rank 2 like free like vector bundle is a different G bundle on P1, right? But they all like are isomorphic locally.
Well, keep in mind that they're all trivialized on X minus a point too. So they come with a trivial. So essentially, so the data is not just a G bundle, it's a G bundle plus a trivialization away from a point. And then we're restricting it to a G bundle on the formal disk plus a trivialization on the punctured formal disk. So, I mean, I will say, like, what's up, Charlie?
I think you helped me understand.
Yeah, I mean, I will say, first of all, that, like, I am not super familiar with, like, just G bundles on different Riemann surfaces in general. So I'm not sure, like, exactly how restrictive the fact that we have a trivialization on X minus a point is. And I will also say that this should be a surprising result, but it's true. Okay, any other questions about this?
Yeah, I guess before I gave the mic to Charlie, so is there some intuition for why we did, like, it seems like the Afghan Grassmannian, at least to me, sort of like came out of nowhere when we expected it to be like some moduli space of G bundles. Is it, yeah, how did that come about? You sort of were like, you know, like, oh, if we're going to recover this as like a moduli space of G bundles, then the following should happen.
So you're asking, like, why we even want to recover it as a moduli space of G bundles?
Yeah, I guess.
Yeah,
sure.
I mean, I think that's a very fair question, sort of as it stands now. So I will say the answer is ultimately because it's necessary in the proof. So it turns out that I'll just give a slight spoiler and say when we get to sort of proving that the convolution structure is commutative, it's going to be something that's sort of only possible to do using the G bundle formulation. But there's also, like, a lot of other reasons why we want to think about the affine Grassmannian in terms of G bundles. Like in Xinwen Zhu's paper, he just sort of defines the affine Grassmannian like this. Just to give, like, one example, like if we have a G bundle on a curve, we can sort of think of these elements, we can think of these, so we can call them raviolis, the guys which were like a G bundle on two disks glued together away from the origin. We could think of that as a local modification of a G bundle on a curve. We can sort of we can sort of place it onto a curve. This is obviously very unrigorous, but we could sort of place it onto a G bundle on a curve and thus sort of replace the curve that was there with, like, we can replace sort of the D1 version of the bundle with the TU2 version on that bundle. So I don't know if that was super clear, but we can, these G bundles on these two disks stuck together, we can think of those as a way of locally modifying G bundles on curves. I guess maybe
I see. And so then the G bundles on these formal disks, like there's some associated, like, double coset thing associated to them, and then that will sort of make up the affine Grassmannian through these Schubert cells. Is that the idea? Okay.
Yeah. Also, like, I'll just say, like right now, maybe it's not so motivated why we would want to think about it this way, but, like, maybe it's not so motivated why we'd want to think about it the other way either. They're just sort of two different ways we might think about it, and they'll both turn out to be useful. In fact, I was going to give a third way to think about it. And I think I'm still going to. Okay, so I'll just say this one's short, and this one is not relevant to geometric Satake. But last way to think about GRG. This way is only going to apply to G equals GLN. I'm pretty sure I could apply to other matrix groups, but it's going to be needlessly complicated. So one thing which I think a lot of us probably know is that GLN sort of bundles are in correspondence with rank n vector spaces. So you can sort of go from a rank n vector space to, like, what's called, like, a bundle. I think someone just said something.
You mean rank n vector bundles? Or?
Yes, rank n vector bundles, precisely. So this sort of way that we're thinking about the affine Grassmannian over here can actually sort of be rewritten in this case as GRG, where again, this is just for G equals GL, is sort of E a rank N vector bundle on D, and beta is a trivialization on D star. But D, let's recall, is just spec of K of formal power series. So what is a rank N vector bundle? Well, it's just E is just a rank N module over these guys. And then we want to take its restriction to D star. Well, how do you take a restriction algebraic geometry? You tensor with sort of, well, if everything's affine, you just tensor with global sections of the thing you're restricting to. So E, let's call this guy M also, but E restricted to D star is literally just M tensored over power series with Laurent series. So we get maybe definition 3 of the affine Grassmannian, sort of M a rank N vector bundle. No, that's exactly what I don't want. A rank N module over power series plus an iso of M tensored with power series over Laurent series with the trivial and rank N vector bundle on D star. And what's that? It's just the module KT to the N. So this isn't going to be relevant to proof geometric Satake, but I think it's very cool because it's a sort of purely algebraic model for what this guy is. Also, it's worth noting that once we have this identification at the bottom, we can think of all these rank N modules as already embedded inside Laurent series to the nth power. And then we can even recover our original definition because sort of GK, or I'll even write GL and K sort of acts on rank N K TT submodules of Kn with the stabilizer GL and O. So yeah, I mean, if you have a submodule of Laurent series the nth power, we can clearly just act on that by n matrices with Laurent series. And if you pick, say, the trivial lattice, just power series the nth power, the stabilizer, that one will be GLN O. So we sort of recover our first definition. The other reason why maybe this definition is especially nice is because it actually gives us a really easy way to prove that the affine Grassmannian is an in scheme. Because we can sort of take our closed embeddings or our closed sub varieties to be sub modules with sort of bounded powers of T on the generators, both above and below. And actually then if we look at each one of this, so if we take sort of GRN, say, to be sort of modules like this where the power is bounded, we'll see that each of those cells actually looks like a Grassmannian, like a usual ordinary Grassmannian. And that's kind of where the term affine Grassmannian came from. But having said that, this last way is more of like a fun aside, whereas the first two will be very relevant.
Sorry, Alberto, can you say again, like what cells are actual Grassmannians in this last
so
version?
these would sort of be like new cells, but we could sort of say, like GN equals M in GRG such that like I'll just write like T negative N times K T. Yeah, so this is unfortunately, so this should definitely not be the same number for both of these. So let's maybe make that M. But yeah, so you can sort of bound the degree of the generators and thus get like subvarieties of the affine Grassmannian. And each of these subvarieties, each of these will just be an ordinary Grassmannian. Because or maybe like a power of like a direct sum of a few ordinary Grassmannians, because you're basically picking the generator in like a finite dimensional vector. The generator's in a finite dimensional vector space now. So this gives us, and you can take like GR equals like the colimit of like GRN. So that's one. That's, for example, how Zinwen Zhu shows that it's an N scheme. So yeah, that's one utility of this way of thinking about it. Does that make sense, Kenny?
Yeah. Thanks.
Okay, cool. Cool. Any other questions? Okay, well, since it's, I think now is maybe a good stopping point. I had one last thing I was planning to talk about, but we can just push that to tomorrow because it's a bit of a, or maybe I'll do a sort of a preview. Tomorrow we're going to sort of put another stratification on the affine Grassmannian where we let S lambda equal. So N is the unipotent radical. So maybe we can say what this is tomorrow too. But and T lambda equals N minus K. And we're going to sort of tomorrow talk about this new stratification and its closure relations and how it interacts with the stratification that we already described. And that's actually going to, it's definitely surprising, like just the way it's written right now, but sort of their interplay is actually what's going to show us that cohomology is a fiber functor. So remember Saad sort of talked about how the way we actually prove this, even though we haven't mentioned today, is by using Tanaka formalism and showing that the Satake category is basically has a fiber functor and satisfies the other properties of Tanaka formalism. That fiber functor is going to be cohomology. And tomorrow we're going to sort of think about that. So yeah, maybe that's a good stopping point. Does anyone have questions about stuff that happened today?
I have a question.
Yeah.
Oh.
Yeah, sure.
Is the affine Grassmannian affine?
The affine Grassmannian is definitely not affine. In fact, not even the Schubert cells are affine, but they are simply connected. So that's something. This doesn't really matter, but they turn out to be like affine bundles over partial flag varieties. And you can actually even figure out what the partial flag variety is from like looking at the co-weight. But yeah, it's not affine at all. The word affine comes more from the fact that like in geometric rep theory, whenever you're sort of dealing with Laurent series and power series and stuff, instead of like C, you often add in the word affine to say things very, very basically. But yeah, is that a fair answer?
Like affine Lie algebras.
Yeah, or yeah, like affine Katzman algebras and stuff, which we're actually maybe going to talk about a bit tomorrow if we have time.
I see.
I missed something really early on.
Yeah.
I think like on the second page, you were looking at the co-roots. Let's see.
I was looking
Yeah,
at what?
so yeah, what this T of K, yeah, it's exactly this. How are you thinking of that as an element of T of K? So
Yeah.
K is the Laurent series, right?
Yeah. So K is Laurent series, and T of K is just sort of the torus with coefficients of Laurent series. So if you have,
Oh, okay.
yeah, if you have a co-weight, then it's sort of a map T. It's exactly like a map, like the one I have sort of here at the top of the page. It's a map. T goes to T to some power in each component, because the torus is just like C star to the n. And then if you just take those T to those powers in the same components, you'll just naturally get an element of the torus with values in Laurent series. Like, just to give maybe the simplest example, like if you look at the unique, or the one which you usually take as the unique positive coroot in SL2, which is like sending T to this matrix, like that matrix itself is just an element of TK.
Okay, so but these are very special elements of T of K. It's not like you're going to be getting arbitrary.
Yeah, these are very much not all the elements of TK, but what we did show is that the geo orbits of them give you all of TK. So that's sort of this lemma/example, right after we define the affine Grassmannian, where we said that if we take just a torus, then the affine Grassmannian of the torus is just co-weights, and it's just given by the geo orbits of those types of points. So yeah, if we take a reductive group like the affine Grassmannian is some like crazy infinite dimensional thing, or maybe not, it's infinite dimensional. And I guess in this case it's also infinite, but it's like the affine Grassmannian of a torus is just co-weights. But in general, yeah, there's tons of other elements in TK which are not of that form.
Okay, great. Thanks so much.
Sure.
So maybe I'm like stealing your thunder for tomorrow or the next day, but you have this crazy way of saying that the affine Grassmannian is like it's like two G bundles. No, that's G of K. Can you tell me how to convolve two G bundles with like as in the affine Grassmannian?
So
wait, first can you tell me again what all right, never mind, you're at the right place. So
yeah.
you have you start with two G bundles on D and two trivializations beta, say 1 and 2. How do you convolve?
Well, so the affine Grassmannian, we can just take it as you have like a single disk with a G bundle on it, and then you have a trivialization on the puncture. So for GK, we need to be a little bit more complicated. So it's going to be a little bit, yeah, honestly, it's going to be like a little bit involved. Like, I mean, we're going to need to, so you remember sort of when Saad was talking about convolution, he sort of drew, yeah, we'll go through all this in like, more detail, but Saad sort of drew a diagram like this.
Yeah, I know the diagram.
Yeah, so, well, if I remember correctly, so we're going to have sort of, so we're going to have like GRG plus GRG goes to, we're going to have upstairs, we're going to have this, and then we're going to have GRG like this. So basically
on the left in that last term, I think.
What's up? Yeah, I'm
the last term on the right should be GK. Oh no, I meant the balanced product should have a GK on the left.
Oh yeah.
The one in the bottom. Sorry.
Wait, what?
When you pass to the quotient, you don't change the objects. You just check a
Oh
question.
yeah, well this is the squiggly thing is, yeah, that, I mean, that's fair. Yeah, Tom, I think maybe that question is actually just best left for when we get there. I mean,
Sure.
if you want, we can like talk about it like after, but it would just be like me going through something that's going to be like a long thing, like today after the talk. If that makes sense.
Thanks.
Yeah, sorry, but hopefully you'll have a satisfying answer on Friday.
Yeah, cool.
Any other questions?
I guess to make sure I understand what the Laszlo Boville theorem?
Yeah.
So is the way that I should think about this, like, okay, if you take G to be like GM and you take X to be like an elliptic curve or something,
Yeah.
you know, like for most line bundles on the elliptic curve, and let's say you take like the point at infinity, or like large numbers of them, you won't be able to trivialize them away from infinity. So is the reason why this is sort of, you know, like this is even plausible at all, is that like what ends up happening is that like most G bundles on X, you just won't even be able to trivialize away
Yeah,
from.
I mean, I think that's accurate. Like off the top of my head, I don't like know exactly like stuff about sort of line bundles on elliptic curves very well, but like, but yeah, I think it's clearly the fact that there's a trivialization away from a point is like carrying a ton of weight here. If so, I mean, I would sort of, the way I think about this is that like in this situation where you have a G bundle on a curve and a trivialization away from the point, all the data is local, is sort of the way I tend to think about it.
Okay, thanks.
I think Surya might have a question in the chat. Okay, so, oh, okay, never mind. He's just answering Tom's question. Okay, great. Yeah. Okay, nice. Tom got a general formula for convolution. Yeah. So I will say one word about convolution, which is just you can literally do what Saad did, and that'll give you a definition of convolution, which is correct. But that will not be that will not be sufficient for, or at least that's not how they prove it. They prove it by modifying the diagram and thinking of everything in terms of G bundles. Well, they use both ways for certain things, but the main insight was thinking of stuff in terms of G bundles. But yeah, okay. Cool. Any other questions?
Can I just keep belaboring this Boville Laszlo thing?
Yeah, sure. Yeah, definitely.
So say X is P1 and let this, and G is GM, and so if E is the trivial bundle, then a trivialization is like
it's a section. Yeah.
Right. And so
a trivialization is always a section for a G bundle. They do the same thing.
So if X is infinity, then a trivialization is just a polynomial.
So,
and then that will turn into that maps to G bundles on the formal disk, which I think is a Laurent polynomial, or maybe we should say x is 0. So then you say like polynomials with negative coefficients now map to Laurent series. I don't know. I just like, it just really doesn't seem like a bijection. I mean, I believe you. This is like not supposed to seem obvious, but
yeah.
I guess I'm saying like trivializations that extend all the way to infinity don't seem, they're definitely different than trivializations only on a formal disk, right? But maybe the point is like, if my trivialization, say I start on the right-hand side, so I have a trivialization on the formal disk, so some like Laurent series, then that actually determines which G bundle on P1 it came from? I have to look at like what
yeah, because
order.
it has to be trivial on the complement, in the entire complement of X. So it's like all you're allowed to do is glue on the trivial G. I mean, this is some articulation of like P1 is obtained from gluing everything aside from 0 and the formal disk. And what's the union? Well, it's the punctured formal disk. You have like a gluing square, like a push out. And if it's going to be trivial on the complement of 0, and you already have a trivialization on the punctured formal disk, then you can only glue those I mean, all you have to do is glue over the punctured formal disk, and then you get your thing that's trivial over the whole complement of 0.
Okay.
Yeah, I think Charlie also.
I don't know if that
I think.
makes sense.
Yeah, I think part 2 maybe somewhat addresses your question. I think it says a very similar thing to that. Yeah.
Okay.
I mean, these 2 parts are often like, usually people just take one of them as the theorem and the other one as a corollary. But yeah, like you can get all the G bundles by gluing one on the disk and one on the complement point. Yeah.
Oh, okay. Oh, that makes sense. Sorry about that.
No, definitely opposite of sorry. All right. Any more questions?